And I would like to respectfully acknowledge that the land on which we gather, it is traditional Mi'kmaq territory. And NSIS acknowledges with respect the diverse histories and cultures of the Mi'kmaq people of this great land. And I am thrilled this evening, as the seminar coordinator for NSIS, to have our speaker join us all the way from Victoria, BC, who thankfully is joining us online this evening. And I'm very excited about the talk this evening. And our speaker, Dr. Saurabh Chitnis, please tell me if I said that correctly.
Chitnis.
Chitnis, thank you.
Yeah,
I'm so sorry about
Chitnis is in channel,
that.
as in TV channel yeah, the channel tunnel.
Thank you. Dr. Saurabh Chitnis
Yeah.
thank you, is joining us from the University of Victoria, where he completed his PhD. He continued on to be a postdoctoral fellow at the University of Bristol and the University of Toronto, and started at Dalhousie University in 2018 and became in 2023 the Killam and Sloan Research Fellow. And then in 2025, became a Canada Research Chair at the University of Victoria. And this evening, we are going to be listening to the work that he was completing at Dalhousie University. And we're very excited for his talk, which is titled Matter from Air, Replacing Carbon with Nitrogen for Sustainable Materials. So without further ado, please welcome our speaker this evening.
Well, thank you so much, Alana, for inviting me, and thank you everybody who's attending. It's really meaningful for me to be able to join you for this seminar series and present in it after having seen several of these in the past on the YouTube playlist. So it's a real honor for me to be featured here, and I hope that it's worth your while for having attended this at 7:30 in the evening. So, as Alana said, I am coming to you from the University of Victoria, which is on the traditional lands of the Lekwungen speaking people, as well as the Songhees and Esquimalt people. And because my story is a little bit complicated, I have summarized it here as well. I wasn't sure if how much of an introduction there would be. So most of the stuff that is over here is already covered by Alana. As she mentioned, I started my career in 2018 at Dalhousie University, and almost everything that I'm going to present today was done at Dal in the first 7 years of my career there. And I've just about 6 months ago relocated to the University of Victoria, where my family's from, and taken on the Canada Research Chair in Inorganic Polymers and Materials. But I continue to have very robust ties with Dalhousie as an adjunct professor. In fact, I have a group there that's comprised of several graduate students and a postdoctoral researcher as well. And I also have a group at University of Victoria, which is comprised of a postdoc and a couple of grad students and undergrads. You can see their names here. I always like to acknowledge all their hard work before getting carried away describing it, because these are the names of the people who did much of it. So, as Alana said, I'm going to talk to you about sustainable materials. And it's a good idea to take stock of what an important development this has been in humanity's history. They really have, since World War II, completely changed the way we construct objects around us. So for the longest history of hominin species, we were using naturally found things that we would shape into useful tools, for example, a bowl or a cup, right? So we would use stone, we would use wood, we would use bone, we would use plant material like leaves and bark and so on. And these are abundant. They're often quite robust, particularly things made out of stone. But they also have limitations. They can be quite heavy. They're, in the case of things like wood and straw, quite flammable. They can fracture easily. So generally speaking, you make them and you either use them till they break, or you throw them away and make another one or grab another one because they're so abundant in nature around us. And so, this was true for the vast majority of human history. With things like metals, glasses, and ceramics, you could address some of these challenges. So metals in particular, they are not brittle. They're actually quite flexible when you heat them. They're ductile, malleable. You can hammer a sheet into whatever shape you want. For example, a metal bowl as shown up top there. Um, but they undergo rusting, right? So they can decompose over time in the environment. There are things like glass and ceramics that are not susceptible to those things, but they have their own challenges. It's fragility and fracture sensitivity and so on. So it's actually an underappreciated development going from the first two to the center point here. What a big change it made, but it's only underappreciated, I think, in the context of people who are not really familiar with tool usage has evolved in humans. This is sort of the stone and the wood age, or the natural found material age. This would be the manufactured material age. And in the European specific context, there's even names like Bronze Age, Iron Age, and so on. Now, these are fantastic objects. They've lasted for centuries, but you can appreciate perhaps that these require exceptionally high temperatures to reshape something. If you want to melt that bowl down and make a spoon out of it, you have to reach 1,000 degrees. Ceramics are even more stable, ceramics and glasses. We're talking about multiple thousands of degrees to get anything to happen with these. So you make them once and then basically they're set like that forever, or they use a lot of energy. Here's another bowl. This one combines transparency so that you know what you're drinking. It's not fragile, it's actually flexible. It's very lightweight, and you can shape it as many times as you want. This is a plastic bowl. The reduction in weight alone has huge environmental consequences. We pay far less in energy to move our stuff around now than we did when we had less stuff, because that less stuff was made out of heavier materials. Right? But plastics are lightweight, so we cost less energy to move them around, for example. So these synthetic plastics are really have revolutionized the world, and they're found now everywhere: consumer goods, implants, within your body, for example. You can't really have glass implants or stone implants inside your body. Right? It's not really going to work. Metal implants, only some metals are suitable inside your body. Ceramics are not at all suitable. Construction, transportation, paints, coatings, absolutely everywhere. So, you could be sitting in a chair like this if you're in a big auditorium or small auditorium. And these types of plastics are made out of polymers, right? So you may know some of these names, you may not know, but the exact names don't matter. Polypropylene, polyvinyl, polyethylene, and so on. Or maybe you're sitting on a couch, and now the fabric cover of that couch is also going to contain polymers, usually a lot of cellulose or cotton, but also a lot of polyesters and polyvinyls, as well as some polyurethane if there's any waterproof coatings on there to protect against spillage and so on. You could be watching me on an iPad or some kind of a tablet. Now, this would be made of a composite synthetic material, but that would also contain, at some point, layers of polymers like polypropylene and polyethylene combined with metals like magnesium, aluminum, and various alloys. Or you're looking at me through a contact lens, and contact lenses are made from polysiloxanes, which is a polymer of silicon and oxygen, which is very, very soft and supple, also used in all kinds of household objects like oven mitts and so on. Or maybe you're not watching me at all, but listening to me through, whatever earbuds while you do your dishes using a sponge that's made out of polyurethane. So, the sponge that you would use to do your dishes is also a polymer. And you can appreciate actually that, particularly shapes like this would be very difficult to make with anything that is metallic or glass or concrete so it's there are some shapes that are just impossible to access or very difficult to access with anything other than polymers. So these are all polymers, these things with poly in front of them, as the name might suggest. Well, they're themselves made from smaller units called monomers. So let's again go back to that plastic chair, which is a synthetic object. I call that a synthetic object because as soon as you see it, you know it's been made by a human. If you were to find this in a jungle, you would immediately know that someone has been there, right? So if you take this and actually zoom way down into this, What you would see is with a very, very, very strong microscope, you would see a bunch of long chains that are entangled with each other. That those would be chains of polymers combined with other polymers and additives to give the plastic color, for example, or to give it some kind of durability towards temperature or fire retardancy or so on and so forth. So this is an object, this is a synthetic material. If you could zoom down even more, and we have microscopes here which do that, what you would find is, and this is one of the few chemical structures you're going to see in this talk. Okay, I've intentionally made it not very chemistry heavy, even though it's a chemical topic. What you would see is a long chain of carbon atoms. A a fantastically long chain, millions of units potentially in this chain of carbon atoms connected to each other. And this is a polymer. Okay, this little N next to this bracket just means that you're repeating this carbon-carbon connected segment many, 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 many times over, millions of times over. And so where did this polymer come from? Well, that's where the word monomer comes in, because polymers come from even smaller building blocks, which are interconnected to make polymers. So the monomers are interconnected to make polymers. It's a little bit like a crude analogy would be Lego bricks. I'm sure you've seen this in the context of a lot of chemistry talks. You have your single brick, which is a building block. You can make complex ones, and then you can make, your synthetic object, which would be, in this case, looks like a Hogwarts castle. Okay, so that's what monomers are. And we can ask now, well, where do monomers come from? Right? We can keep going. Well, this is where the trouble begins, because monomers come from under the ground. At the present, at least. More than 85% of them actually come from petrochemicals. In fact, this is the fastest growth sector for a lot of petrochemical industry. Actually, because energy usage, use of petrochemicals for energy is going down as renewables is coming up, but we still rely upon them for making all the materials in our world. And that means, extraction infrastructure. So in this case, a rig or a drill that would get it out from hundreds or thousands of meters underground, as well as processing infrastructure and facilities that take the stuff that's been extracted, put in a lot of effort and technology to purify it, enrich it, and convert it to a form where it becomes usable. But it is fundamentally, this is an extractive industry. It's a one-way extractive industry, and it is digging this stuff from under our feet and putting it onto the surface and into the air. We can ask now what happens at the end of the life of plastic, because the monomers that we get out of them get turned into polymers, and then the objects that we use, and then something has to happen to them when we're done using them. Well, the news there is not great either. I'm going to show you a graph here. There's going to be a lot of text on it that's quite small for you to read. Don't panic. It's not important. The only thing that's important is the size and colors of the bars, because I'm going to walk you through it as if you can't read any of the text. Okay. But I just give that preamble because it's a busy figure. So here's that figure that I told you to not panic about. So on the far left, you have all the different types of plastics we make: polyethylene, high density, low density, polypropylene, PET. So you don't need to know all these names, although you may be familiar with them from just, your recycling bin, for example, or your recycling infographic. Now, that's the far left side. It's showing you, based on the width of those bars, how much of that plastic is made in raw form, and then where it ends up going in society. So, for example, a lot of it goes to packaging. A lot of it goes to electrical equipment. So the insulation for wires, for example, right? Wires have to be insulating. Building and construction materials. A lot of plastic is used. Some of the biggest uses of plastic is construction, transportation, and so on. Now, the thing I want you to focus on is the far right-hand side, because the far right-hand side is telling you what's happening to it at the end of its life. At the end of its life, this much is chucked into a landfill. Okay, this much, the part below it, is actively used, so it hasn't been thrown away yet, but stuff over here, or its uses are not known, but the stuff over here is thrown into a landfill. This bar over here, this box, we don't throw away, but instead we burn for energy. So this is quite common in European context, for example, incineration of plastic, so you can extract the energy out of it. Just like you would burn oil, which is long chains of carbon, you can burn plastic, which is long chains of carbon, very long chains of carbon. And this little box here, less than 10%, is what's recycled. So this is why it goes back into the beginning over here. So it's a complex figure with lots of information, but the point I'm trying to make is we start off with this much and we recycle this much. Okay, so this is not a good situation. Um, the stuff that ends up in the landfill is going to be there for a very, very long time because synthetic materials, plastics in general, are not biodegradable. And that's for a very good reason. It's because biology has not yet evolved ways to break down long chains of carbon, right? Plastics have been around, mass-produced plastics have been around since the 50s. And evolution is slow. Plastics are just too new for this. So it's too difficult for these to be broken down. So what are we left with? We're left with something that is difficult to get access to because it's deep underground and it requires a great deal of effort, energy, cost to access it, plus something that is really not recycled in any meaningful way, but mostly just tossed out, plus something that does not degrade on its own. Okay, so the combination of these three things mean we are effecting one of the world's largest one-way transfer of carbon from underground reservoirs where it's trapped to above ground and atmospheric locations where it will persist with harmful effects on the ecosystems. So for this reason, I claim that carbon-based synthetic materials are currently not sustainable. So what can we do about this? At least when it comes to synthetic materials, the three R's still hold true. Can reduce, reuse, and recycle. There's a lot of nuances to this. Often, it's not possible to reduce usage. It's for social or political reasons or even moral reasons. It is difficult for a country like Canada, which is a huge consumer for many decades, to turn to a smaller country that is just developing to say that no, you don't deserve that quality of life because you choosing that quality of life is bad for the environment. But we use we've been living this quality of life for a very long time, but you don't get to do that. So there are limitations on how much reduce is effective. As the world's population become increasingly more able to access resources, it's difficult to tell them to not use them. But there are efforts underway to replace plastics with alternatives like PLA and PCL so that you reduce your dependence on fossil fuel plastics. So these are plastics that are easier to access in a renewable way from biomass, corn, and from other thrown away biomass. Alternatively, you can replace them with more sustainable things like paper and wood. But again, these have limitations, as I mentioned, going back to, so waterproofing, for example, is an obvious one. Right? Waterproof paper is actually just paper with a polymer coating on top of it. You can reuse things. Clothing is a great example. Many clothing polymers can be reused entirely, so they can be used for the same purpose to make new clothing, or you can, completely change them and turn plastic bags into carpets, for example, or plastic bottles into carpets. You can recycle them physically. You can melt them and reshape them. That's actually one of the big advantages of plastic is you can easily reshape them into something else, which you can't do with metal or glass. Or you can chemically turn them back into monomers and then repolymerize them into something useful for you. And engineers and scientists are working on all of these fronts. Okay, this is a huge area of research in Canada and around the world, and one that I think is very, very important, as important as all our efforts to make sustainable energy, in my view. A lot of time and effort and money goes towards discussion of sustainable energy, but actually sustainable materials is just as important because even if you get all your energy from renewable sources, you can't really justify shutting down the fossil fuel industry or even mitigating it because we are dependent upon them for the stuff we make objects out of. So while people are working on these, we're taking a very different and radical approach, one that is a much longer term, which is to completely rethink from the ground up the elemental basis of the way we construct things. So this is a very blue skies approach that will not work over the short term or medium term, but requires a long timeline. But it is fundamental chemistry that is paving the way for this as even a possibility, whereas it was not before. Someone's got their mic on. Just I'm not sure if they want to, and I don't want them to accidentally say something that they later regret. Okay, so what's our approach? Well, we looked at nature and saw that nature extracts its monomers from air, right? So a tree will take CO2 out of the air and turn it into wood. Well, can we do something similar with synthetic materials? Of course, we could just use wood, but wood has limitations, as I mentioned already. It's flammable, it's hard, it's opaque. You know, you can't make thin films of it, you can't fold it easily, and so on and so forth. So it absorbs moisture. Can we, instead of digging underground, constantly looking beneath our feet for monomers, can we look up in the air for them? And we think that we can. Because what is air? Air is a mixture of gases. The vast majority of that is nitrogen, N2, right? That's this molecule shown over here. 78% of it is nitrogen. And you're breathing it in right now, breathing it out. It has no effect on your, day-to-day metabolism. The rest is oxygen, argon, carbon dioxide, and others. And I put carbon dioxide here because, this is approximately 400, well, of course, it's more than 420 now. This is, the CO2, we're worried about this, and as you rightfully should be, but just you compare that to how much dinitrogen or nitrogen gas we have in the atmosphere, right? 780,000 parts per million. So this is a good thing that there's a lot of nitrogen because it's a key part of biogeochemical cycles. So there is at least a biological chemical cycle that takes atmospheric nitrogen, turns it into components that are used by plants to make food. And just to give you an example, the reason this nitrogen is incorporated is because nitrogen is the main element found in amino acids and proteins. So plants, as with all living beings, they require proteins. So they get their nitrogen to make amino acids and proteins out of it. Animals then eat the plants, decompose, and return that nitrogen back into the soil, where it's again either released into the air or it is re-uptake by plants. So there's an existing cycle for moving nitrogen around in the ecosystem. By the way, this cycle does not exist for carbon, right? And I'll explain that in a moment. So there's a lot of it around us, and it's very accessible, and it can be cycled through the ecosystem. And it's for this reason that I believe the nitrogen is the most abundant, accessible, and equitably distributed resource on Earth. So I've talked about abundance, accessibility, and recyclability. Let's talk about equitably distributed. The second law of thermodynamics prohibits you or any other country or any despot or dictator from hoarding all the nitrogen in the world. You cannot do it. Entropy will stop you. Gases cannot be separated easily from each other. And so, a child born in a slum somewhere has the same access to nitrogen as a billionaire on their private jet. It is the most equitably distributed element on Earth. It's also very easy to access because you can capture it from the air. Now, none of these things are available or true for carbon, right? Carbon is locally abundant in some places. It's not easy to recycle. That's why it was in the ground for millions of years until we started to dig it out, right? It doesn't automatically come out of the ground very easily on that timeline. It's certainly not equitably distributed, right? There's 8 to 10 nations that dominate the fossil fuel cycle, and it's abundant, but only for a short time. It is a terminal resource; it will get ended, and because it cannot be cycled through very easily. The reason for that is that plants don't need carbon from the ground. They're getting that from the air. So if you take some carbon and you bury it in the ground, well, it stays in the ground. Okay, so what can we do with nitrogen? Well, there are four requirements that you need to unlock its usage in materials. The first is that you need to convert nitrogen into a usable form. The reason there's so much of it is because it doesn't react with anything and get used up. We need to put a lot of energy in and combine it with a different molecule, hydrogen, to make something known as ammonia, which is ultimately what we use. And this is a process that is known to humanity. We make 250 million metric tons of ammonia every year for fertilizer. But we need to make this using green energy. Otherwise, it's not sustainable. We need to take ammonia or ammonia-based molecules and turn them into polymers. The problem with that is that nitrogen-rich molecules tend to be explosive. They want to be nitrogen gas again. This is not ideal for making materials, right? You want your materials to be stable. The third thing is that they have to have some useful properties. If they don't have useful properties, they won't be used. So, the reason we use carbon-based plastics is because they're very useful and they have useful properties. And finally, they have to be degradable. We have to develop the science required and understandings required to reuse them in a natural way. So for the next 10 minutes or so, 10, 15 minutes, I'm going to walk you through how we are addressing these challenges, or not just us, actually. The first challenge we're not addressing, we're addressing challenges 2, 3, and 4. Other people have already made progress on challenge 1. I don't want to give you the impression that we've solved all 4 problems. We're not there yet, but that is where we're headed. So let's talk about the first problem, making useful things from ammonia. And this actually making ammonia from nitrogen in the air in a green sense. This actually starts with hydrogen, because you can make hydrogen by using renewable energy and water. So we can split water, which is abundant on Earth, to make hydrogen, and as a byproduct, oxygen. Well, this hydrogen and nitrogen, as I've mentioned before, can be combined to make ammonia. This is, like I said, one of the biggest industrial processes we have already been engaging in. If we were to take this ammonia and combine it with methanol, which is also known as wood alcohol, which itself comes from carbon dioxide and hydrogen. Carbon dioxide we're trying to get rid of. Hydrogen we can generate in a clean way using wind energy or other renewable sources. If you combine methanol and ammonia, you get something known as methylamine. Now, those of you of a certain vintage may remember methylamine from Breaking Bad, but we're not going to do anything related to drug making out of methylamine. I'll come back to this in a moment. You can also take ammonia, turn it into something known as hydrazine using peroxide, which itself comes from hydrogen and oxygen. You are not going to be tested on this content. You don't need to worry too much if the chemistry is complicated. The only thing I want you to keep track of is that we can turn this hydrazine into a molecule known as 1,2-dimethylhydrazine. Yeah, methylamine and DMH. The important part is that up to here, we have been carbon negative because we removed carbon dioxide from the air. And we are also generating all our energy using renewable sources. Now, as I'll mention later on, this is not a pipe dream. This is already happening. In fact, it's happening in Nova Scotia. So the reason we care about these two as the end result is because these are fossil fuel free, carbon negative nitrogen, 1 nitrogen and 2 nitrogen monomers. You can think of them as Lego bricks. This is a Lego brick that's 1 nitrogen long. This is a Lego brick that's 2 atom long. So it's a single brick or a double brick. But importantly, these bricks were not made with fossil fuels, right? They were made using carbon dioxide and green energy and hydrogen. So they're analogous to the fossil fuel building blocks that we currently build our world out of, methane and ethane, but they are carbon negative. So this is something that is happening on an industrial scale in Nova Scotia. So there's multiple projects, Point Tupper, there's projects by Everwind, World Energy, GH2, several companies are using wind energy for this. So I'm going to say that smarter and more capable people than me have already addressed this challenge, and this is not for me. The next challenge is how do we make stable molecules? Well, it turns out that methylamine and dimethylhydrazine, which I showed you as the building blocks, cannot directly be used to make stable entities. Because when you make polymers out of them, long chains like this out of them, they explosively decompose back down to monomers or to two nitrogen chains. So this is not good property for materials. And this is where our discovery comes in because we recognize in 2022 that if you put nitrogen into three-dimensional structures instead of two-dimensional or one-dimensional structures, then it becomes a lot more stable. As an analogy, you can take a piece of paper and you can tear off a small strip of that paper. Okay? And that small strip of paper is kind of like a one-dimensional string. Now, if you have a very thin strip of paper, you can flex it and bend it in many different ways. And it turns out that this flexibility ultimately makes the polymer a little bit less stable because it can achieve configurations that are explosive. Not good for materials. So if you do this with nitrogen, one-dimensional chains, that's no good. Take that same sheet of paper and you have it as a sheet, you can notice that when it's a two-dimensional object, not just a one-dimensional object, it's flexible in 2 dimensions, but not so flexible in the third dimension. That's good. That's a little bit more stable. Take that same sheet of paper and you roll it up into a tube. Well, now this tube is rigid in both dimensions. And that's an analogy to what we do with the chemistry. We turn nitrogen chains into nitrogen cages, and they become far more stable and don't decompose as much. In fact, they become 5 times more stable. This unlocks everything that I'm going to talk to you about. Because now, for the first time, humanity has access to nitrogen as a building block. We never used it as a building block before. This is unlocking a new resource. So this is what the cages look like. Again, you don't need to understand any of the chemistry. Just look at the numbers. These cages are 36 to 42%, 28 to 42% nitrogen by weight. And they do not blow up. They are extremely stable. For comparison, TNT is 21% nitrogen. And that famously blows up. So even twice the amount of nitrogen, and they are still stable. And that is the dimensionality effect, going from one dimension to three-dimensional. The way we make these cages is by taking nitrogen containing units and stapling them together in three-dimensional shape using phosphorus. This is another atom that is from the periodic table and an element from the periodic table. So don't worry about the structures. Just know that this is what they look like in case there are some chemists in the audience. So can we build stuff from them? Yes, we can. And I'm going to show you some examples of nitrogen-rich materials that are perfectly stable. By nitrogen-rich, I mean they are less than 50% carbon. For a comparison, most commercial polymers are anywhere from 70 to 80% carbon. Ours are less than 50%. The rest is nitrogen predominantly. So we can make films. So this film, this transparent film on the left-hand side, looks, feels, stretches, and acts exactly like cling film in your kitchen because you want to make replacements that look, feel, and behave the same without having the negative aspects. So that's intentionally. You can make a transparent film or you can make a cloudy film depending upon how you make it. You can make an opaque film. So this is approximately looks like 15 centimeters long, 6 inches long circle that was cut out of it's got the consistency of cardboard, right? So it's a thick plastic or cardboard. We can make powders. In many cases, polymers are preferred as powders because then they dissolve faster or they can be pressed more easily and so on. We can make powders as well. We can make rubbery objects. So this is kind of like a gel-like material. We can make objects that have interesting properties. So they can, this one, for example, we call noodle. This is a polymer noodle which swells just like spaghetti does when it absorbs moisture, or a diaper would upon absorbing moisture. And then you can go back and forth, back and forth. So we can shape them to make solid objects as well. Now, I'm intentionally not going into a lot of chemistry, but for those of you who are interested, there's a lot of open access journals in which we have published, or open access publications that we have on this topic, and we can get that full reference from the recording later on. So I'll just mention that we are well on our way to making stable, non-explosive objects. I've just shown you several examples. This is just a small assortment. These things have to be useful. And I've already shown you some examples. So we can make things that have tunable opacity. So if you want to make a see-through window or a see-through coating, you would use a plastic like this. If you want to block some vision because you have a fishbowl office with lots of glass, well, you would use a cloudy coating on top of that like this. There's also some interesting electronic properties. Again, don't need to worry too much about the details of this graph. All this graph is showing you is that compared to the industry standard, which is BOPP, our polymers are better insulators. So one of the major uses of plastics in the electronics industry is as coating around copper wires because they're insulated, right? So they insulate the wires from each other. Our plastics are better insulators at both low and especially at high temperatures. This is important for wires because sometimes wires get quite hot. So you want them to be insulating even at high temperatures. And we have just found that ours are, they easily beat the state of the art in insulation at high temperatures. There's also some interesting properties. For example, our materials are intrinsically flame retardant. So what I mean by that is that you can take a Q-tip, the left-hand side of which is not treated with our polymer, and you'll notice that this starts to burn. And this is going to keep burning until it reaches the polystyrene, or the plastic thing in the middle, and then that's going to burn. But the side that's coated with our polymer really does not catch on. You have to keep igniting it, and it keeps going back out, keeps going back out, keeps going back out. Right? Eventually, of course, if you keep trying to burn it with a butane torch, it will catch on fire. But if you look carefully, you'll notice that it's the top that catches because that's where the commercial plastic is. Okay, and then the bottom falls off and the top continues to burn. So nitrogen-rich plastics are also intrinsically flame retardant compared to carbon-based plastics because of they also combine with phosphorus to make a non-flammable phosphorus nitride. So there's interesting properties that we can unlock, and that's point number 3. We can engineer. I'm only giving you a very small assortment of properties. There's many more that we are developing and studying in collaboration with other research groups because we're the fundamental chemists. We come up with the idea and do the proof of principles, and then we work with collaborators and industrial partners to develop applications. The last point here that I want to speak about is degradability. If you go back to the natural nitrogen cycle, this is a key premise in our approach that nitrogen should be able to move through biological systems in a way that carbon just cannot. And in fact, we already do this. So industrial farming is critically dependent upon fertilizer. Doesn't even have to be, big scale farms, even small scale local organic farms, even they use compost or manure. Well, the reason we all do this is because compost, manure, fertilizer contain 2 elements that are absolutely critical for plant growth, nitrogen and phosphorus. In fact, the requirement for nitrogen and phosphorus is the basis of ammonia production being the world's largest industry because we take that ammonia, we combine it with phosphate to make fertilizer. And that's why your bag of fertilizer might say N and P on it, besides something else like potassium, for example. This is a critical aspect of modern existence. We need fertilization through commercial fertilizer or composting or manure to be able to feed 7 billion people. There's challenges with this, of course, runoff and so on, and eutrophication that comes from that. But suffice to say that there is already, at least in theory, a mechanism in place that would motivate the reasoning that nitrogen and phosphorus-based plastics should be degradable. And so we thought, well, if our materials contain nitrogen and phosphorus, could they serve as slow release fertilizer? That is to say, you take the piece of plastic, you bury it in the ground, and it slowly releases its contents back into the soil. And by slow, I don't mean 1,000 years, which is what is the case, not 1,000, but not, I don't mean hundreds of years, which is the case for a plastic water bottle, but weeks or months maybe. Okay. And so this is a hypothesis we're testing now with our materials in these grow boxes on the Truro campus at Dal with my collaborator Lord and Michelle, where we're growing tomato plants that are fed our plastic in the soil during different phases of their growth to see how they perform. And indeed, what we find, I'm not going to go into the details here or reveal the exact identity of this for intellectual property reasons, but compared to the negative control and the positive control, which is fertilizer, in some cases, we don't see much improvement. So in this case, for example, we were measuring the length of the leaves that were formed. And that's, it's neither here nor there. At least it's not harming the soil. We can say that for sure. If anything, it's slightly improving the outcomes, but nothing to write home about. But in other cases, the results are dramatic. Some of our polymers actually outperform even the commercial fertilizer. So this, for example, is how many tomato flowers are going to bud if you give a commercial fertilizer versus our polymers. I should say these are early results. We don't understand why this is the case. Okay, I'm not a plant scientist. That's my collaborator. We don't know why this is the case. So a lot more work needs to be done to understand why that is. So I can't explain to you why that is. But all of this is to say that there's at least compelling proof of principle that we can make degradable materials. And not only are they degradable, but they can actually serve as something useful, fertilizer in this case. So now let me talk to you about some challenges. I've talked to you about how we solve some challenges. There are some that remain. First, manufacturing costs. Polyethylene costs like 85 cents a ton. And if that number changes by 5%, entire industry shut down. All right. Ours cost a few dollars. So we are way away from making this affordable at this stage. But we've only discovered this 2 years ago, right? 2, 3 years ago. Safety, it takes a long time to establish the safety of any material. That you cannot rush this. You have to do this slowly and carefully. Processing cost. One is manufacturing, so there's the manufacturing cost, but there's also the cost for making, for example, molding plastics and recycling plastics. All of that is significantly high right now and requires different infrastructure. But these are things that my team is working on already. We're already working on all three of these and making good progress. There's an entirely different set of issues. There is the collective failure of humanity to be able to even recognize that plastic waste is a problem. This was a spectacular failure just a couple of months ago, where we, after getting quite close, failed to, well, I guess a year ago now, failed to secure an agreement on a global plastic waste treaty. There's the influence of existing fossil fuel industry. Oil industry is very powerful, and oil-rich nations are very powerful. And there's a conflict of interest here that is very obvious. There's also the case there are bigger problems in the world. Although because I devote my life to this is a big problem for me, and I believe that it should be for a lot of us because we're continuing to pollute our environment. When you are treading water just to stay afloat, you're not worrying about, if I should make a boat out of sustainable materials. You're just going to get onto a boat. Okay. But these are not problems that science alone can address, and this is where we need the humanities. This is why we need humanities to be able to, know whether we're doing the right thing, even if we can do it or not. But I don't worry and stay up at night in despair, because these are all challenges that were true for the petrochemical industry and plastics based on them until World War II. All it takes is one compelling proof of principle, proof case. In the case of carbon-based plastics, it was the use of plastics in World War II. They were lightweight, easy to transport, and durable. That made them extremely obviously useful before things took off. So, I firmly believe that science measures its progress in decades and centuries, not so much in months and years. And so I'm not worried about it, but it needs a lot of work. So let me then leave you with the long-term vision. And I start that long-term vision by first showing you what is the current state of the art. The current state of the art is that we use fossil fuels to make energy. We use it to make ammonia. This is one of the biggest industrial processes undertaken by humanity. It's to make ammonia. It's about 2% of global energy usage. We turn into fertilizer, which then turns back into nitrogen. In the process, we emit a lot of CO2. We also take fossil fuels, we process them to make carbon-rich materials, plastics, which get buried into the soil or pollute our environments, or get combusted into CO2. So this is overall driving a one-way mass transfer of carbon from underground to above ground. Instead, we envision something where we use hydrogen and nitrogen as the basis of our civilization. We use this for making energy. We use this for making ammonia. We can use this to perhaps, and this is where we step in, also make our materials by taking something that we are already making on a spectacularly large scale and finding another use for it. Okay, to combine it with a gas that we want to remove from the atmosphere to make nitrogen-rich materials and turn them into fertilizers. By the way, at least the first part of this is already happening, right? So like I mentioned, there's projects like Everwind, Bearhead, World Energy. What's interesting is they talk about green hydrogen, but in reality, what they're going to make is green ammonia because hydrogen is very difficult to ship. So at least in the near term, it's much easier for them to convert that hydrogen on site into ammonia, liquefy that, and use 60, 70 years of existing, government policies, infrastructure, shipping policies, and so on to ship the ammonia, which then will get broken back into hydrogen or burnt. And I'll just mention I don't get any money from them for mentioning their name. I mentioned this purely for informational purposes. I wish I got some money for them because I feel like I'm adding value to their product, which currently they're setting on fire. Anyways, so I'll just end with that vision, a vision of completely reshaping the elemental basis of our built world. This is going to take time. Um, it has taken time to even get here, and I'm grateful to the students and postdocs, as well as the undergraduate students who have devoted their precious time and put their hopes in this vision to move it forward. I'm also extremely grateful to Dalhousie University for giving me a chance to get a good start on this project, and I continue to work there remotely with a substantial team to push this research forward with lots of collaborators as well, who I list some of whom I list over here, as well as a variety of funding agencies. And finally, I'm grateful for your attention and time, and would be very, very happy to answer any questions. Thank you.
Thank you so much for that presentation. That was awesome. That was,
Thanks.
there are some questions online that I am does if you have oh Tanner has a question. Maybe I'll go with Tanner first.
That was really great to see, Sarah. I've
Thanks,
not
Tanner.
heard a general talk review, I think, but that was exceptionally well done. Yeah. Appreciate that.
Thank you.
The one question I had, this kind of tied 2 points of yours together. If you could go back to the slide that had the flowering on it.
Oh yeah. I think that was 5. Yeah.
Yeah, this was like one of those like jaw-dropping kind of
Yeah.
things. And again, I know you mentioned preliminary results are
Yeah.
always like this, or they can be, but if this does turn out to be the case, I do think your statement that you're not making drugs may not be right because it seems like you made a growth vitamin.
Yeah. 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 It's hard to know what the mechanism for this process
Yeah,
is, right? This is, I mean, I just have no expertise in plants, and it's a very steep learning curve for me. And actually, in realistically, I think it'll take multiple people working on it to understand
yeah,
why this is actually true. But we're excited about it because, consider if you could get two crops in, because if you're
yeah,
potentially flowering sooner, maybe you may fruit sooner. But of course, this all remains to be established.
yeah. Really cool. Thanks a
Thank
lot.
you, Tanner. Yeah.
I just want to get to the questions that somebody put in the chat first. And they are, how are they degraded?
Yeah.
UV through inorganic or organic chemistry? And the
Yeah.
second part is, how stable are these polymers?
Yeah. So I'll answer the second one first.
Yep.
They're stable enough that we handle them in the air. As I showed you, we can't even burn them, right? That's how stable they are. So they're thermally very, very stable, up to 400 degrees, I think. I think up to 350 degrees at least. There's no indication of any degradation.
Mhm.
They're completely water stable. They decompose in strong acids. They will decompose. They're not affected by electrical discharge. So, stability is like a 50-dimensional question, but I'll just say that in all the standard places where you use plastic, like something like polypropylene or polyethylene, they are perfectly stable. Now, the previous question before that was about how do they degrade?
Mhm.
Well, they certainly degrade in the soil,
Hmm.
even under normal room temperature conditions. So that tells us that there's something in the soil that is degrading them, which I'm inclined to think is the 500 million-year-old ecosystem whose entire job it is to take anything that has nitrogen and phosphorus and make it into food that plants can consume.
Hmm.
That's really what we're tapping into when we do the soil degradation, is an existing mechanism for degrading them that is way smarter and way more complex than we are in that it's not just one bacterium, it's the entire soil microbiome that can act upon it. That includes viruses, fungi, bacteria, and there's many of them that can break down nitrogen containing substances.
Hmm. I saw, thank you for that. I saw Helga, you have your hand up. Would you like to ask your question?
Yeah, it sort of joins in with your previous answer. Is in my, I'm an animal physiologist, not a
Uh-huh,
plant
uh-huh.
physiologist, but it seems to me that the whole nitrogen recycling system is an indication of the scarcity of nitrogen in a simple form and its need to be
Yeah,
absorbed and converted into
yeah,
other other living systems.
yeah.
And so one of my worries is, can one saturate that and
Mhm.
make it not be as easy to use? Like right now, there's not enough, but if we were to give a whole bunch of it, will
Yeah,
it slow down effectively
yeah,
per unit nitrogen?
yeah. So first of all, I think our production scales would have to be truly gargantuan for us to make a dent in how much nitrogen there is, at least atmospherically present. We're taking the atmosphere, the nitrogen directly from the atmosphere. We wouldn't be tapping into existing cycles to extract the nitrogen from them. We would be adding to them if we use it as fertilizer or as a precursor to fertilizer. The difference is we are doing that, or the point I would emphasize that we are doing that already right now with commercial fertilizer that we just
Exactly.
make and put
Yeah.
in the ground.
Right.
We would
Right.
just not do that. We would then
Right.
just use the materials we make. The challenge is that depending upon the shape, the size, the thickness, the surface area to volume ratio of the piece of plastic, it will degrade at different rates.
Hmm. Hmm.
That's a big problem because it's hard to standardize that. So what would have to be done is something that is done for fertilizer right now commercially, which is to say the particle size is standardized. You can get fertilizer that's really fine grained. You can get fertilizer that's big chunks, and they have different applications. So I think in terms of upsetting the balance, it would be possible to just cut down on the stuff we just make to throw in the soil that way. That would be my guess. Yeah.
That makes sense. And I had to think of the mycelial network that connects
Yeah.
so many organisms and is
Yeah.
transferring materials between macroorganisms
Yeah.
like trees from one tree to another and stuff like that, which is
Yeah.
just there's
But we
just
are
so
very
much
sensitive to
going
that.
on. We don't know much about
No,
what's
we
happening
don't.
in the soil. It's
But
just
but you raise a very good point and one that we are actually carefully looking at, including doing genetic studies to see how the soil genome is changing, whether some species are overexpressed, underexpressed due to our addition, whether certain nutrients suddenly disappear because we've added this in. So exactly what effect this has on the soil microbiome. I'm not an expert in that, but my colleague Lord Abbey is, and so he will be looking at that as part of this because it's a very important point.
very, very interesting study.
Thank you
Thank you
so
so
much.
much. I really appreciate it. I thought it would be full chemistry and hard to understand,
No,
but
no,
it's
no.
great. Thank you so
Thank
much.
you.
I see that there is someone else. Tudor, you have a question? Can you unmute yourself?
Hi, that was a very interesting
Thank you.
presentation. Um, yeah, it happens that I'm also a plant scientist.
Oh, good.
But actually, my question is why you never try first to grow bacteria with this molecule as the only source of nitrogen?
Hmm.
That is usually what people are doing. You can try a consortium of bacteria and then you provide your compound as the only source of nitrogen. And then you can see how it is getting degraded. Then you can go either way. I'm not sure if it's you are going to be reduced or oxidized.
Hmm. Hmm.
But that is the way I would go, definitely before going for plants, because plants are growing in soil and you don't know what happens. So soil will secrete
True.
some compounds, but definitely you are dealing with a soil microbiota.
Yeah.
And most people, when they have these compounds, it's even not really recommended to start putting mixing with soil. It's probably better to use as the only source of nitrogen. You try to grow bacteria and you see what happens because you can go through intermediate compounds that can be environmentally unfriendly.
Yeah. Yeah.
And
So
you say that can be strong acids or whatever. I'm not
yeah.
sure. I hope you're not generating nitric acid, but
No, 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 no. No, it doesn't become nitric. It doesn't become generate acid. It decomposes if you put it in concentrated acid, is what I
yeah,
meant.
but you have no idea how they decompose.
I
They
mean,
get oxidized, they can reduce. What happens?
These molecules would be the phosphorus is already fully oxidized in them. It's not going to get oxidized any further. The nitrogen can be oxidized further. That's what's happening. They're getting oxidized. So it would have to have access to oxygen or other oxygen-rich species somewhere in the soil to be able to do it. But let me answer the bigger question here. Of course, yeah, there's a different way to do this. A more controlled way where we do this in the lab with very well controlled experiments where we add exactly, we keep track of everything we're adding and control the medium tightly. I just don't have expertise in that, and I haven't been able to entice somebody who does. So I
Yeah,
think the
no,
idea is
yeah,
very
any
good.
microbiologist can do because
Yeah,
you have nitrosomonas, you have nitrobacter, you
that's
have
true.
you have bacteria
Yeah,
that will go either way, will
yeah.
oxidize or will reduce, and you just provide this source of nitrogen and you see what happens.
Yeah. So I think this is a great study. Our 5-year plan, so to speak, was to get compelling reason so that we can go attract somebody with that skill set to say, hey, we've got these results. These would be really exciting. We would love to reveal this, broadly and be able to fully understand what's happening. But right now we're in the phase of the work where we're still getting just something interesting that we would then be able to go to then
Yeah,
say, okay, here's
why I'm
now
saying this,
motivation. Here's
why I'm saying
motivation to do a controlled study.
Yeah, why I'm saying this because nitrogen, if you provide to plants a lot of nitrogen, that will promote the growth, will not promote flowering.
Yeah, that's a good point.
So
Yeah,
it promotes just the vegetative growth. You put a lot of nitrogen. That's why we are faculty of agriculture. I'm from faculty of agriculture. That is a very basic knowledge.
yeah,
You are putting a lot of nitrogen. You not have too much flowering.
yeah.
Uh,
But it's also
so
phosphorus.
has to be something like this, and maybe it degrades in something that promotes that. I cannot say that,
Yeah,
but then probably the best, because it's very hard to isolate the products of degradation in soil and in premix, what the substrate. So that's why I would say that
yeah.
uh,
I
if
agree.
a microbiologist could do that
Yeah,
and provide your compounds as the only source of nitrogen and see how they are degraded, I would say
yeah,
that is a much faster, very
yeah,
precise, very productive as science, publication, impact,
yeah.
and so on.
That's a great idea, and I completely agree with you. And I would be happy to receive suggestions, or if you're volunteering yourself, we're happy to send you many
Well, we
specific
have here
samples.
at Faculty of Agriculture, we have microbiologists, and we
Yeah,
have chemists involved
sure.
in.
Yeah, I need to do a bit more looking and see
Yeah,
who
sure,
take
no
the bait.
problem. Yeah.
But now I've got this presentation and I've got you
No,
on
it's very intriguing.
suggesting. Yeah,
I
cheers.
was really looking because, yeah, nitrogen, it's a very hard molecule to cope with.
Yeah.
It's so reactive, so unstable. So the fact that it's something it's a, I can imagine that's a major achievement. Now, obviously, it's the initial input of energy is much higher than in the case of carbon.
Oh yeah, and I think it's in part because we have not optimized this procedure. We have just discovered it. There also isn't, 60, 70 years of optimization behind it, nor is the real cost of energy paid by people who use fossil fuels, right? So they're not paying the true cost, they're paying a highly subsidized cost. And there's also economies of scale that we're not tapping into because we're making things on, gram scale or kilogram scale, not ton scale. So I think the cost thing is the easiest one to address. There's it may still not be cheaper, but at least we can work on that. Yeah.
It's
But thank
just
you.
from environmental point of view, making sure what are the degradation intermediates, it's probably crucial.
I agree. Thank you. That's really
Okay.
a valuable point.
So any other questions before we bid farewell to our speaker? I just want to double check that I'm not missing anything. While I'm looking, I would like to read you some comments online.
Oh, sure.
That was an excellent presentation, very accessible, interesting and impactful. Thank you. Thank you very much. And
Oh,
Jillian Phillips, the president of NSIS, commented and said, on behalf of the NSIS, thank you for an interesting presentation. As a non-chemist, I really appreciate your presentation approach to make this accessible to a non-specialist audience. And I echo everything that Jillian has written there. So thank you so much for a really fascinating presentation and for joining us on the East Coast from the West Coast.
Yeah, my pleasure, and thank you for all the compliments. It's a real pleasure to be able to do this, and I am firmly of the belief that us doing all the science as scientists is only as important as people who can communicate that to a broader audience. So I'm grateful for your organization's efforts in that direction because I think the world is not short of good ideas. The world is short of people who are getting those ideas to where they need to go and into the right ears and into the right levers of power. So I think what NSIS is doing is fantastic, and I'm grateful to be able to help in that mission.
Well, we're certainly glad that you were able to join us this evening, and thank you to the audience for joining us. And don't forget, this talk will be available online, so you can watch it again, and we can all learn even more. So thank you so much for everyone, particularly our speaker. Have a great evening.